This is Kosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen, to Kosmographia, the Randall Carlson podcast. I think we're on episode 60.
That's right.
Episode 60. Made it? That's right. Hard to believe. And many more in the future. No plans to stop. Right, guys?
At least 100 more.
Yeah, at least. What do you think, Randall? You got maybe another 7,000 shows in the hopper?
Well, I was actually thinking this would be our concluding show.
Of course.
We're gonna shut it down after this. No, 7,000. That sounds about right. I'm thinking 7,200 because that's twice 3,600.
Of course.
And 3,600 is the square of 60.
Right.
So
72.
Yeah, that's very predictable logic there. So 7,200 episodes would be. Let's see. So if we did 7,200 episodes,
we're not quite 1%.
At one a week, right?
Yeah.
Right. Okay. So that's that's 138 years worth of shows. So I think we're gonna have to pick up the pace a little bit.
Testing somebody's longevity there.
I think we can do that. I can do this for 130 years.
138 years.
138 years. Yeah, I could do that.
That's a good goal.
Yeah.
So we'll still be podcasting in 2020, 200 something.
So what did we say? 138. So 2021.
So 2158.
Yeah.
21.
59 maybe.
Yeah. I think we can do that.
Right.
Well, there you go. 21, almost to 2160.
2160. Come on, just round it off.
We'll just round it up.
Well, we got to allow that we're going to take a few weeks off, so we'll probably finish in 2160.
Okay. All right, there we go.
Done.
Well, I think last week's episode with Ben and George was fantastic.
That was a lot of fun.
Yeah.
Sure was, yeah.
Man, we got to get out to Egypt.
Yeah, man.
Yeah, I'd like to get back there. You know, there was just, what I realized even after 2 weeks there was, I saw there's more things that I didn't see than I did see.
Yeah, of course. Yeah. It's like that everywhere we go, right? Every trip we take to go look, even if whether it's geology or ancient structures, there's just not.
There's always more that we didn't see than we did see.
That's right.
That seems to be a general rule.
Right. The world is large.
The world is large.
And time also is large in its extent.
Yeah, but God, it seems to be going by quick.
Right. Well,
and you know what? And I'm sure Mike will back me up on this. The longer you go, the quicker it goes, it seems. I mean, a year to me now is like, once upon a time was like a month. It seems like,
right.
Last month when I was, no, that was last year.
Yeah. Whereas when you're like a little kid, one summer day stretches off into infinity, right? It's like,
yes, it does. Stretches off into infinity.
I don't know, with all this COVID stuff, things just seem to be stretching off into infinity, don't they?
Yeah, in some ways they do. It does seem to be stretching it out.
Yeah, because it's not even a year that we've been fighting, struggling.
Yeah, it just feels like forever in this.
It seems like multiple years, definitely.
Yeah. That's true.
Well, we won't get into politics. I can easily segue into politics.
Good call. Yeah, let's not.
And at some point, Mike and I have been planning. We haven't told you about this, but we're planning a major
insurrection.
Debate. Yeah, and we're going to do kind of the format like who was it used to be? Remember Sean Hannity and who was the other guy? The liberal side.
Alan Combs.
Hannity and Combs. Me and Mike are going to do our version of that.
Great.
Awesome.
Except, wait a second. Does that mean
The beard side chats.
Randall and Waz.
Randall and Waz.
Carlson and Waz.
Problem is I don't identify with conservative or liberal. I'm transcendental.
There's a trans word again.
No, transcendental, Mike. That's
okay.
Not.
I think you're also.
That's different. That's different. That's not part of the whole gender politics, Mike. This is transcendental.
Yeah, and Randall's also he's quantum offensive, right? Right.
That's right. That's
right.
right.
We had an email on our show about a guy who was saying he did quantum aggressions. Quantum offensive. He was both offensive and not offensive at the same time,
as opposed to microaggressions.
Yeah, it's quantum aggressions.
I like it.
Okay.
Yeah, he's in a superposition depending on the observer.
Yeah.
So I like that.
Well, I'm tempted more and more these days to indulge in mega aggressions, just because we've got to have some balance here.
Yes.
Hey, but folks, there are some things out there that really are worth getting offended about. There are actually some things, but yeah, let's see. The first time I heard the term microaggression, I honestly thought it was a joke.
Yeah.
Oh, they're joking, right? Somebody's, the Onion, or, somebody is, making light of something. And then I find out, no, that's real.
They're serious. Yeah.
They're serious. Ooh. Okay.
Yeah. Well,
I see. When I heard that, I thought to myself, yeah, I think the apocalypse is a little closer than I thought it was. So
the end is nigh. You heard it here first, folks.
Yes.
Speaking of apocalypses, where are we going? What catastrophes are we looking at today? Past catastrophes.
What's the lesson?
We're moving around because I'm trying to give the broad view so that folks live in all these different places, traveling these different places, will begin to appreciate how ubiquitous and widespread these features actually are, with the general idea that everybody's got something in their backyard, if not right under their own feet, that's left over from these mega scale events. And so we don't have to travel far to see some of it. Although if you want to get the big picture, it requires traveling around to the various places. And of course, that's ultimately the goal, is to try to convey the big picture. But so what we're doing is we're kind of visiting these various areas. We've been talking the last episode before last about the southeastern area, particularly in the Appalachians. We had that important discussion. We got chastised, and I learned something. And you know what? Living in this area, I should have known better, and I really did know better. But because after all, my mom's people are Appalachian people. They settled in 200 years ago in the southern Appalachians. But people who live in the Appalachians pronounce it Appalachian, and all the outsiders pronounce it Appalachian. So
gotta keep that in mind. It's going to be tough.
Got to keep that in mind.
Yeah,
it's important. Well, it is. And so, what's behind Brad there is actually the Valley and Ridge province, which we're going to talk about. But so we started looking at some of the studies, the geomorphic studies. I'll say our last episode, we kind of, because we didn't get into that with our swapcast with the boys, with George and
Ben
and Ben, George and Ben. So, but we were talking about some of the papers, and just to kind of a quick summary and review of what we were looking at. We'll just take a minute to run through it, some of it. We talked about the John Hack and John C. Goodlett paper from 1960, which was one of the earlier ones, where they were looking at the Little River, Virginia Valley, and there had been evidence of major boulder transport in that particular valley. And they said the transportation of coarse debris, which is the major work of erosion on the valley floor and sides, are accomplished during major floods that have a very low frequency of occurrence. So very low, we found, as we'll go through here, that very low may mean 10,000 years or more. There was, he was talking about looking at evidence that there had been major mass wasting events along the mountain flanks where massive amounts of bouldery debris and so forth slid down into the valley floors. And we're attributing that to oversaturation of the mountain flanks by excessive amounts of rainwater. So then he points out, and this is an underlying part of that study, they say there is a limit to the amount of runoff that a forest can withstand. So in other words, if you've got a slope and there's a forest growing on it and you have enough rainfall, it's intense enough, the ground becomes super saturated, boom, you're going to have a mass wasting event and the whole forest essentially can slide down into the valley. And as early as 1960, I think this was a bit of so it showed some prescience here. They were a little bit ahead of their time, Hack and Goodlett. So in their conclusions, they're saying that the writer's interpretation of the landforms of the Little River is based largely on processes that are observed to be active today. And then we looked at the reference that what the processes that they were looking at today were these very intense storms that had occurred. Now this is 60, so this is not yet the James River flood from the Hurricane Camille in 1969, but they were referring to this Little River flood, which was an earlier intense flood in the Little River Valley that accomplished an extraordinary amount of geomorphic work, but over a very limited area, see? And so they're using that as an analog and saying this extraordinary flood that happened in the Little River Valley that produced all this geomorphic work and possibly triggered major landslides and mass wasting, showed that there were processes like that active today. But in order to explain, what we learned was that in order to explain the ancient deposits, they had to invoke the most extreme modern deposits that we've experienced in historical times to try to come up with some kind of an analog. So then they go on to say, and this is the prescient part, on the other hand, it is probable that large climatic changes of worldwide extent have taken place recently enough to have had an effect on the processes that produce the forms that we see. So in other words, you go to a specific example, a specific section of a river valley, and here's the evidence of a major, in this case, a major intense rainfall. And then you have flooding, you have debris transport, you have mass wasting events. It's in a very localized area. But then you're seeing that provides an analog for the much vaster, widespread geomorphic effects that appear to be essentially the same genesis, the same type of origin. So from the limited local, they're extrapolating to something much wider. And the fact that they were willing to say large climatic changes of worldwide extent, I find that to be pretty interesting to be coming from a couple of geologists back in 1960. Then we jumped ahead to 1969. Daniel McCallick, fan-like features and related periglacial phenomena of the southern Blue Ridge. Now, what does the term periglacial mean again?
Close to the glaciers.
Close to the glaciers. Now, this is relative, but, we say periglacial in the southern Blue Ridge because you had to go up to basically Pennsylvania to get to the glaciers, but that could still be considered periglacial compared to, say, now, for example. You could not say that there's any glaciers, major ice sheets or glaciers within, 500 or 600 miles of the Blue Ridge province of Virginia now. But so in that paper, he attributes it to a past interval of intense physical weathering. So obviously, if you've got great ice sheets, 500, 600, 700 miles to the north, and then they extend for another 1,500, 2,000 miles beyond that, and you're in this periglacial region, the periglacial phenomenon is not going to be limited to a single watershed, for example, but it's going to be, it's going to be very widespread throughout the whole southern Appalachian regions, right? So what he's doing is falling back on the explanation that, well, we see this phenomena, it's very widespread, but he's still resorting to the idea that it somehow is connected to the unique environmental circumstances that would be associated with close proximity to a major ice sheet. And so he's attributing it to the intense physical weathering extending over a broad region that's a result of the periglacial location. And then he cites the block fields, block streams, and other block accumulations, which are common features in many parts of the Blue Ridge province. Goes on to point out that they are unseen by the average traveler because most of them are remote from the main highways. And we'll be looking at some pictures of those in a minute. And they are concealed by forest and brush. And then he says that such block concentrations are often located on the headward parts of fans and on the adjacent headward slopes. We went into some detail to explain that the debris fans, of course, they form wherever the material in a flood is sweeping down a constricted valley and it opens up towards the valley floor. And as it opens up, the rush of water that is confined to a channel is going to be moving faster. When the gradient, gets less, and the channel gets wider, the water slows down. And as it slows down, it begins to build these debris fans because it's laying down its material. So it's important, I think, or significant to note that these many times, as Michalik here is pointing out, the block fields and the block streams are found at the tops of the fans, which would make perfect sense because that is now, even though he's attributing it to a past interval of intense physical weather, and clearly what it's showing there is that water is the most likely agent of transport and construction of these features. He says wherever there are high ledges or cliffs, there are found usually are block accumulations below, okay, which would be mass wasting. But in many cases, block fields are found in places where there is seemingly no good reason for their existence. Well, I would think there, basically what you're talking about is a fluid, almost a fluid, a viscous fluid that's supercharged with sediment and carrying in training a lot of large boulders. And because of its low viscosity, it's able to move over very low gradients and then spread out with a very, very, like I said, very low gradient. And that's what I would attribute that to. He finally says, though, that the emplacement of blocks on fans presents a problem. And here's the problem. Because he's looking at what's going on there today, and he's noticing that there are the modern streams are relatively small. So he says it is difficult to conceive how small streams, particularly with the small drainage basins available, could have carried large blocks to their present positions under any imaginable conditions of discharge. So you can see the resistance there to what they're looking at. You've got this phenomena. It's beginning to take on the appearance of, wide scale fluvial erosion and deposition on a huge scale, but it's on such a scale that it's outside the conceptual framework of geological thinking of 1969. And then he refers back to Hack from 1960, the paper we referred to earlier. And he says of major significance in Hack's 1960s paper is the contention that periodic floods of extraordinary severity have formed most of the landforms of the Little Creek area in Virginia, and by implication, similar features elsewhere. So the problem of the frequency of recurrent is the frequency of recurrence of floods of such magnitude. So then he looks to modern analogs, and he looks at cloudbursts, where you have a very short but very intense rainfall over a very limited area. And then he says, now, unless it can be shown that these cloudburst floods actually build fans and accumulations, and of course, this is what the James River flood did when Hurricane Camille stalled over the headwaters of the James River, was that you could actually have floods of such intensity, rainfalls of such intensity, that it could begin to recreate these archaic landscapes, right? He says, however, unless it can be shown that these cloudburst floods actually build fans and block accumulations, or at least to appreciably enlarge existing deposits, merely to multiply the frequency of these deluges will not allow for their formation. So you can see he's struggling there. He's going, yeah, well, some people say there were these huge storms, floods that resulted from these storms. But the problem is that this scale of the phenomena that we're looking at is so vast that what are we doing? We talked about this problem last episode, is because, right? So you've got a local event here, then you got another one here, and you got another one here. In order to recreate the entire field of these things, the entire area in which these deposits and these features are existing, why we need hundreds and hundreds of local events. So are each one, are they, see, so here now that brings up the question, okay, if we've got, let's say, 100 different local events, we look at 100 different catchment basins of streams, and each one has these features that appear to be megaflood derived, right? Well, do we go, okay, well, each one of these is a discrete event. You know, we had one here, and then what, maybe 100 years later had one over here, and then one here. Or are they all the consequence of a single event?
Well, that's what my question is based on. If you looked at all these on a map, are the catchment basins adjacent to each other? Or are they actually spread? Are there a lot of catchment basins between them that don't seem to exhibit these same features? So
far, the answer to that seems to be no.
Okay. Because, yeah, that definitely looks like one big event, or maybe a few large events back to back or something.
Mm-hmm. And then he points out in that particular paper that even the modern floods that occur typically, you know, every year I can go over here to the creek near where we live, and about once a year there will be a pretty darn big flood. I mean, there was one this fall. We had 3 days of rainfall, and I can tell. And sometimes we'll have a year where the stream does not rise to the point where it goes outside of its main channel, but I think maybe since I've been living here, it's done that at least 3 or 4 times, which means that we're, you know, looking at 3 or 4, maybe 5 times, because I can always tell if I haven't gone over there during the peak discharge in the creek channel. You know, there's a dozen different ways where you can see the high water marks, because oftentimes you'll see, you know, if there's a little shred of something, there'll be something carried in the water, and then particularly in areas where you have vegetation, you'll be able to see leaves and branches and stuff that have been carried down in the floodwaters. And in the case of this, because it's flowing through the city, there may be a piece of plastic, there may be some tissue paper or whatever, and you can see it up in the tree branches, you know, growing up on the floodplain, up on the terrace. You know, okay, you realize, okay, the water was up that high. If it comes up out of the channel and spreads out over the floodplain, once the water level drops and it goes back into the channel, it'll always leave fresh deposits of sand up that's obvious, because within 2 or 3 years, you know, from just natural processes, if there's a deposit of sand, it sort of gets worked into the soil. And, you know, you can come back the next year and you'll see the layer of fresh sand is still there. Another year, it's still there. But each year you go back, you'll notice that it's getting more and more obscured because there's more vegetation, there's more, you know, rainfall, there's, you know, wind or foot traffic or whatever. And after maybe 4 or 5 years, you'd walk through there and you aren't going to notice it anymore. But, you know, the few weeks or month or several months right after the flood, there's a very obvious layer of fresh sand. I've shown this slide many times where my SUV is parked and you see the sand ripples that are up on the floodplain. You recall that where I used that to show the scale invariant nature of ripples. That was an example of, you know, when Hurricane Ivan flooded the creek channel enough that the water rose up, it rose out of the channel and flooded the entire, there's a park, right? Which is a normal thing to do. You build a park on the floodplain because, you know, the restoration of a park is much easier than a restoration of a bunch of buildings. But you could see very clearly the high water mark as you went across. You could see it on the tree trunks. You could see it on buildings. You could see traces of how high the water got. Able to measure it and found out, you know, that maybe 100 feet, 150 feet back from the edge of the stream channel, the water was flowing 2 feet deep up on the floodplain.
Right. Down where we are, our river has a whole bunch of cypress trees down right on the banks. And some of them are just huge. And the most noticeable thing to me after we had the serious flood was you could see the flood shredded the bark. You know, it was all really fuzzy bark where the floodwaters were coming through. Mm-hmm. And then above that, it was nice and pristine. And it was just way up there, like 30 feet up. Those tree trunks was just shredded. And of course, there's like stuff stuck in the trees up there.
Yeah.
And it was so, like that for, I remember being able to see that mark for a year or two, maybe more.
Yeah. And so, obviously, with a bit of observation, you can quickly reconstruct the high water mark.
Yeah.
And I found it particularly interesting because in this case, I could measure the amplitude and wavelength of the sand ripples as a function of the water depth. And by using the Chesi formula, which is just a simple formula that relates water depth, gradient, and a roughness coefficient to the velocity of the water flow.
Yeah.
So now, you know, if you've got the high water mark and you've got the gradient, now you've got the basics that you need to solve the formula.
I also think it's interesting that, you know, you're talking about, so we have, you know, you have a regional or a local flood, and the after effects of it are visible, you know, depending on it's really the scale of the flood that details how long it takes for the signs to go away.
Mm-hmm.
And so here we are on this podcast looking at a flood that happened 12,000 years ago, and the signs are still around. That tells you the scale of the event we're talking about here. You know, you got a local flood that can cause millions and millions of dollars in damages, but after 4 or 5 years, most of the signs of it have completely disappeared.
Mm-hmm, mm-hmm.
Well, we're looking at something that happened 12,000 years ago, and the signs are still there if you know how to look for them.
Yes. Yeah, that's right. And it's because of the scale of these ancient floods.
Yeah.
Obviously, if you have a descending scale of floods, let's say you have a series of floods and each one is smaller than the preceding one, they may modify the earlier features and deposits and so on, but that's all they're going to do. I mean, if you have a flood that can move a 20-ton boulder, any flood that comes along after that is not capable of moving a 20-ton boulder is not going to move that 20-ton boulder.
That's right.
It may move, you know.
It may put a bunch of 1-ton boulders next to it, but it isn't going to move it. Yeah.
Right. Exactly.
Yeah.
So, so Michalik says, it's difficult to conceive of a discharge of water, regardless of the severity of the storm. Sufficient to have choked some valleys with the tremendous boulders that now block them. And we're going to see a succession of photographs to give to convey some sense of that.
But even though it's hard for him to imagine it, isn't it that pretty much what it had to have been, right? What other source of water would there have been but torrential rainfall?
Well, yes, that's exactly right.
Okay.
But
He's just
bear in
saying
mind
it's-
now, this is 1969. And, at this point, they've done well to, for example, accept the catastrophic flood formation of the Channel Scablands. But it'd be almost like, okay, we'll concede that. Just don't require us to think that there might be mega scale floods anywhere else.
Okay.
We'll give you that one. We'll give you the Channel Scablands, okay? But don't expect us to invoke that for something else. However, there's the evidence is so overwhelming. That's where you can almost, as you're reading his paper, you can almost begin to see he's having trouble wrapping his head around it.
He's struggling with it.
Yeah.
Go
ahead.
Well, I just thought that the way he wrote that was, it could have been that he was actually struggling with it himself, or he was very, in a sly way, writing to his peers who, subscribe to the standard model, but pointing out the fact that it doesn't make sense looking at it in their
Could
model.
be. Yeah, it could be.
It seemed like it was, written like that. So he's still accepted.
I might. Yeah. Well, yeah. So up to this point, now we're going to jump ahead to 1981 to Hugh Mills, and he's making some observations on slope deposits in the vicinity of Grandfather Mountain, North Carolina. And again, he's going back to the idea of, in some way, periglacial phenomena. But see, bear in mind that up to this point, geologists haven't been too concerned with that stuff. As he says here in the Mills paper, most of the information on surficial sediments in the southern Blue Ridge province has been provided by geologists primarily engaged in bedrock mapping, right? Because, if you're looking for a hydrocarbon reservoir, you're going to be looking at the bedrock. You're not going to be looking at the stuff on top of the bedrock. See, so really the stuff on top of the bedrock is just basically stuff that's in the way of what you're trying to do. If you're trying to map the bedrock, all of this stuff is just the stuff that's in your way. See, up until this point, early on, you had the geologists looking at the surface features and the landscapes, because that was the first thing that you could obviously see. And we can talk about, at some point, we definitely will talk about William Buckland and Georges Cuvier and Adam Sedgwick and Roderick Murchison and some of these other guys who were the founders of geology. And interestingly, the founding fathers of geology were almost all catastrophists. The gradualism of Charles Lyell and James Hutton came later. And so for a while there, you had two competing interpretations of landscapes. You had the gradualist, the uniformitarian, which, like I said, came from James Playfair, James Hutton, and Charles Lyell. And then you had the catastrophists. But the catastrophists tended to be somewhat older. They were more not so much concerned with establishing some kind of an academic dogma about it. But when universities started incorporating geology as an academic discipline towards the latter part of the 19th century, they wanted to codify with a which makes sense. You try to come up with a set of basic principles that you can work from. And by this time, the uniformitarian idea had proven itself as being very valuable. Yes, we look at modern stuff, and by studying modern processes, we can find evidence of similar processes in the past. What happened, though, as I've explained multiple times, is that as that became a dogma, you see, here is the thing. Here, the problem was with the catastrophist interpretations is it came with too much baggage, and that baggage was theological stuff, biblical stuff, right? And so that was working against it. So when geology became established as an academic discipline, it was easy to just, we aren't going to get into the theological argument here. We're not going to bring that in. So the best way to not do that is just let's not bring in catastrophism, because coming in with catastrophism is biblical literalism on some level. So that was one of the overriding objectives of the establishment of geological science as an academic discipline, was to get away from the evangelical framework of geological, because at that time you still have a lot of people arguing for a young Earth. You know, the Earth is only 6,000 years old, and they were very adamant about it. So there became this sort of this dichotomy that was actually even almost like two hostile camps, right? So now we're trying to establish geology as a science over here, right? And over here they're saying, well, except that it conflicts with the biblical interpretation. So that's kind of what happened with catastrophism. It got left outside the doors of academia because of the fact that it had this monkey on its back, which was biblical literalism, if that makes sense. The problem was then it became overly dogmatic. And we saw that dogmatism fully entrenched by the time J. Harlan Bretz came along in the 1920s, early 1920s, and proposed a catastrophic flood formation for the Channel Scablands. And that was a major breach within the gradualist wall. However, what we've seen, and we'll certainly come to understand this more once we really begin to look in depth at the Channel Scablands and Missoula flood features, is that the attempt was to now constrict the explanation of the Channel Scablands and its origin to a uniformitarian model, which was provided by the analog of modern outburst floods, typically as you would see in Iceland and Alaska and British Columbia, in the Himalayas, wherever you had mountain glaciers. And one of the things that's interesting is that when geology was being, in the 19th century, when geology was being established as a science, right? The planet was just coming out of 500 years, half a millennium of Little Ice Age. During the Little Ice Age, glaciers worldwide grew to their largest extent in over 10,000 years, right? So first phase of the Little Ice Age, early 1300s. It ameliorated just long enough for the Renaissance to kick in, and then another phase of the second phase of the Little Ice Age came in the mid-1600s, caused chaos throughout Europe. In fact, caused chaos around the entire world. And we're going to talk about that at some point, and the consequences of the Little Ice Age, and how the repercussions of the Little Ice Age are still echoing today. And once we understand those repercussions, we can actually see those after effects. But so then you had the Little Ice Age, the glaciers grew. So now, at the same time that the glaciers began shrinking back with the modern warming phase, you have the emergence of observational geology. And so now you have these early geologists looking at, what's happening here as the glaciers begin receding back. They begin to see the landscapes. They could see with their own eyes the creation of terminal moraines, for example. The glaciers now have grown down, and you've had generations of people, let's say, living in the Alps who've been watching the glaciers grow. And they see the glaciers come down, they see the living ice moving, transporting all of this material, and they could watch from year to year and decade to decade the building of terminal moraines, right? Then when the retreat of the glaciers began, the glaciers started back, they leave the terminal moraines as evidence of their existence, right? Now, in the case of the Little Ice Age glaciers, what happened was you had a set of moraines built and then abandoned as the ice retracted. And they were able to go, look at these moraines here in the Jura Mountains. They're just like those moraines down 20, 30, 40, 50 miles down slope from here that are actually much bigger, but apparently have been there for a long time because now they got trees growing on them, right? Well, this led to, let's see, if the glaciers came down here and built these moraines, and then you've got these really big moraines down here 30, 40 miles beyond, That much means that the glaciers must have come all the way down to the valley floor at one time. See, these were the kind of observations that people like Louis Agassiz were making, and figuring out that that there had been a great ice age. So it was very much a result of the uniformitarian principle. Look, we can see what the ice is doing here now and creating these features. And look, here's identical features, but on a bigger scale. So there we go. Now you've got the uniformitarian principle.
It's a good principle.
It is, yeah. Mm-hmm. However, it's only half the equation. See, that's it. And so now we got back to the floods. We're seeing stuff that's so vast and so widespread that it's confounding. It's like, how can this be? I mean, what's the scale here? I mean, it's one thing to think of a 10-year flood and then go another order of magnitude and think, here's a 10-year flood. That's pretty bad and catastrophic. A 100-year flood would be 10 times worse, right? But what happens when you're looking at a flood that appears to be 3 orders of magnitude larger than anything in modern experience? Now the mind kind of recoils at that scale of phenomena. How could that be? How could you have a flood that would wipe out an entire? It's one thing to say, okay, one county, the most catastrophic rainfall in the eastern United States in living memory, wipes out half of a county. But wait a minute, we're now talking about a flood that wipes out multiple states simultaneously. You see, there's a reluctance to want to go there. But the evidence speaks.
Yeah, is there any evidence that geological processes don't scale up to as big as they can get? I mean, what denotes here's where the geological scale stops? Nothing can be bigger than that. No process can be larger or more powerful than this.
Well, when you see, and here's where it gets interesting. Once you get to that level of terrestrial features, you want to go up one order of magnitude more, go to Mars.
Yeah, exactly. That's
but not, I don't think, on Earth.
Right.
I mean, there are limitations, I think, given.
Well, there may be limitations in terms of what has happened. But are there limitations on what could? That's the question I guess I'm trying to get at. Like, why do they have this artificial line where they're like, to this level of energy and no higher are we going to go on these geological processes, because then it's too close to the biblical flood or something like that?
Well, in the biblical flood model, you've got a supernatural flood that basically drowns the earth uniformly up to the highest mountain peaks.
Yeah.
With no explanation of where the water actually came from and no explanation as to where the water actually went.
Right.
So it's hollow earth.
What?
It came out of the hollow earth and went back in it.
That's right.
Oh, was that it? But with the floods we're talking about, of course, we've got a very naturalistic phenomenon. I think we have two sources for what I would call biblical scale floods. One is catastrophic melting of great ice sheets. Now, the thing is if you don't have those scale of ice sheets, you aren't going to have the floods. In other words, the kind of floods that we're looking at here in the evidence for them, particularly when we go north and we're looking at those, river valleys and tunnel valleys and drumlins and stuff that are directly associated with the ice. Obviously, if there's no ice sheet, you're not going to have those floods. You're not going to have that mechanism for creating and generating gigantic meltwater floods. We got that. In other words, what you would have to do is you would have to go to get something equivalent to that, and this even wouldn't be enough. You would have to go and basically melt the entire Greenland ice sheet and the entire Antarctic ice sheet within a matter of, say 5,000 years. Now, and over that 5,000 years, you're not looking at a uniform disappearance of the ice. You're looking at interruptions. You're looking, and this was what gets us into the energy paradox, which is that, if you have 350 kilo Langleys of energy per year in order to get the ice sheet to retract 800 to 900 feet of horizontal wastage and 150 feet of vertical wastage, which is what you have to have in order to get the whole damn 6 million cubic miles of North American ice complex to disappear in, say, 6,000 or 7,000 years, you got to come up with a lot of heat from somewhere. And in the studies that were done in the early 70s, the assumption was, okay, so you've got an average rate of disappearance of the ice over 6,000 or 7,000 years, right? So meaning you've got two endpoints. At one point, you got the ice complex is there. The other endpoint, it's gone. Now, is the disappearance going to be consistently uniform through there, or is it going to be variable? And if it's going to be variable, that means that there are times when there's lower melting and other times when there's higher melting. The higher melting is going to create more discharge, right, and require essentially more energy than if that melting is spread uniformly across the whole 6,000 or 7,000 years. And that's the paradox. So the paradox is that there's no known source of energy, or at least when these studies were done in the 70s, that could melt that much ice that quickly. So to get to 350 Langleys per square centimeter per year, you had to go to tropical oceans. But even tropical oceans were only provided 1/3 of the energy necessary to melt the great ice complexes as fast as they melted. So what that means is if you took the combined Cordilleran and Laurentide ice sheets, and you moved the whole damn thing down so it was peripheral to the equator, so it's in tropical oceans, it's going to take somewhere around 20,000 years to melt the entire ice complex. That's what's known as the energy paradox. And it was first identified in the early 70s, never resolved, and so it was conveniently put on the shelf and forgotten about. And now, with the modern discussions of climate change, nobody has any incentive to pull that thing off the shelf and dust it off and go, wait a second, this problem was never resolved. How the hell do you get rid of 6 million cubic miles of ice in 6,000 or 7,000 years? Duh. But Kosmographia, we're going to bring that question back and put it on the table.
Excellent. Well, I took us off on a tangent there, but do you want to take a quick break and then we'll come back
and look at pictures?
Yeah,
I
All
do.
Right. We'll be right back.
All right.
All right, welcome back, ladies and gentlemen. Kosmographia. Before we return to the material, we, as always, want to mention CBDfromthegods.com. Go check them out on their website. If you make a purchase, make sure to enter our promo code RCShipsFree to get you free shipping, and that really helps out the podcast, and thanks to everybody who has done that. And, everybody on this show has tried it, except Silent Mike.
Except normal guy.
And it's so mean.
He's the eldest amongst us.
Mike is the control guinea pig.
Oh. That's right. It's a true scientific study over here at Kosmographia. We have our control.
We just give him some olive
control
oil.
rat.
Yep, he's still feeling terrible. So we're pretty sure that this CBD stuff works.
Well, I have been out for 3 days, and you know what? You guys commented that I was tired, and you know why that it was? I had a bout of insomnia last night. So,
for the first 10 minutes of having the, getting on the meeting, Randall was.
I'm on.
Yeah.
I was thinking about just turning it over to you guys, and but yeah, honestly, I this is something that it's been a perennial problem with me ever since I was a kid. I have bouts of insomnia where I lay awake all night. I hate that when I'm trying to get to sleep because I have to get up in the morning and do normal things like normal people do. Laying awake all night can be really tough, Even when I was a kid, like in second grade, I'd go tell the teacher, teacher, I got a stomach ache, when I didn't really. So I could go down, and then I would go to the nurse's office and say, I got a stomach ache. I got to lay down for a while. And I would go into dark room there. I would lay down and I would go to sleep. I would do that. That was a regular routine of mine. I think the teacher, my second grade teacher, I think she knew that. She knew that I was, but I had that nap and I came back.
It's Randall's nap
refreshed,
time.
raring, ready to go,
Yep.
But anyways, I've been out. My whole point of this is that I've been out of CBD oil for 3 days. I should have a shipment arriving tomorrow. I'm hoping. No mail delivery today. So I'm hoping the shipment arrives tomorrow because, maybe my first time with insomnia in about 3 months. So that was pretty convincing to me that the CBD oil really is helping me sleep.
Well, a couple of weeks ago, you did the same thing. I don't know if it was a couple of weeks, but you just didn't take it for a couple of days,
right?
And we had to put the show off. So
Yeah.
it makes a big difference. It's obvious to us.
Yeah.
Yeah. Okay.
Yep. You forgot to take it.
Well, yeah, you could tell. Well, you'll be able to tell if you see me here like this. You'll know. You'll be saying, "Well, Randall's not been taking his CBD oil."
That's right.
Yep.
So he's wide awake. Can't sleep at this instant. He sits down to do the podcast. He's like,
he admitted he's moonlighting on us. He's already done 2 podcasts in the last however many hours, and 1 more to go this weekend or coming up.
That's good.
Right.
I have another one coming up. Okay. Well, yeah, I'm trying to get the word out that we're doing this because there's a lot of people who don't know we're doing this yet. So,
Yep.
Yeah.
Good to get the word out.
Got to get the word out. Yeah.
So yeah, one more time, CBDfromthegods.com, promo code RC ships free for free shipping. So great company.
Yep.
Yeah. So during the break, we were throwing around ideas about the subject matter, and Brad, I had a question a couple of weeks ago. Brad brought up that was like, how is there a limit to the size of objects that water can move, that flowing water can move?
Mm-hmm.
And we were discussing that during the break, and you wanted to say something about it.
Yeah, well, right. And what I told Kyle was that what seems to be the limiting factor is the transporting medium, not so much the object itself, because in other words, increase the volume of water and the power of the water, the stream power, if you want to, which it would be called the stream power, which is a function of depth and velocity.
Right.
It's the limitation of stream power that's going to limit the size of material that can be transported. So theoretically, if you have no limit on how much water you could have, I mean, yeah, you could keep scaling up. And really what we would get down to, which I think is that limiting might be, and which is something we're going to explore in an upcoming program, is a bolide impact into an ocean, where you have a tsunami making landfall that might be 200 or 300 feet high. That's going to be pretty impressive. Now, of course, interestingly, we can see boulders of extraordinary magnitude that were almost certainly deposited by tsunami waves. And we've got photographs of those. We're going to get into that. That will be part of an upcoming episode where we look at tsunamis. But there, for example, there is studies have done that would suggest that an earthquake or a undersea volcanic eruption would have a limiting size on the scale of the tsunami that could be generated. And to get bigger than that, you would have to go then to an impact.
Yeah, and that way you also have pressure on top of flow rate. So you got volume, velocity, and high pressure. That's going to be able to move bigger materials and hold them together when it moves them as well.
Yeah, and then you brought up the point that all material will have a characteristic cohesiveness that can be overcome by enough external forces imposed upon it. So depending on the rock, if it's a sandstone rock, it might be very granular. So if it gets transported forcefully, it may end up as sand, right?
Right.
Now, if we go to the channel scablands, that's almost all basalt. So basalt has a completely different way of fracturing. like particularly columnar basalt will cleave along. There'll be cleavage planes that actually will produce, that were originally vertical sections of rock. Or you may have Hackley basalt, which is a much more homogenistically grained type of basalt. Now it's gonna form big, sort of almost spherical chunks, and when we get to the scablands, you'll be seeing photographs of examples of different kinds of basalt, not only as part of the bedrock layers, but also as material that has been stripped away by the catastrophic floods and deposited.
Right, so, and that's all about crystalline lattices and stuff, and the way they're when they're forming.
Exactly.
So you have very organized lattices, and that's how you get the columnar shapes that are very regular geometric shapes, and then you have the stuff that's all stirred up. It's a totally different process.
Yes. So Mills, he was pointing out that he brings up again the idea, and I know this is a bit of a reiteration, but this is fairly complex material, so it doesn't hurt to go over some of it again, because our objective here is not to just throw out a bunch of information, but to actually educate people so that people can really understand, here's the sources of this stuff, these studies that we're looking at, and if the material is complicated enough, it's worthwhile going through it a couple of times to really get it, because we're kind of laying the groundwork here to be able to talk intelligently about these cataclysmic phenomena that essentially have been under-recognized for the last 2 centuries. And so we're entering a new era here of understanding and realizing that we're living on a planet that has been profoundly affected, even on a planetary scale, by these cataclysmic events. So Mills pointed out...
Sorry, Randall, just to clarify, since we are educating, right? So you brought up a new term there that I hadn't heard, so I thought maybe we need to define that. You said a kilo Langley, and then you said something else again about a Langley. So what is that a measurement of?
Is 1,000 Langleys. Yeah, okay.
and what is a Langley?
It's a measurement of energy, right?
Yeah, it's just a measure of thermal energy.
Thermal energy.
Thermal energy, yeah. And I can show you whether, in terms of, you can transform it into ergs, you can transform it into BTUs.
Calories.
Yeah, calories. We'll come back to that. We'll actually
bunch of energy measurements.
Dive back into the energy paradox. And I'm going to show some slides and graphs and stuff to help people get the picture better of what we're talking about. And at that point, we'll dive into defining some of those terms. It's a measure of thermal energy. So in other words, you've got somewhere around 5 to 10 kilo Langleys per square centimeter per year over, say, the area where the ice sheet used to be. And you've got perhaps 100 kilo Langleys per square centimeter per year where the most thermal energy is available, which is over tropical and equatorial oceans. So that kind of gives you a range, right?
Yeah, I guess I'm looking at it. It's especially used to express the rate of solar radiation received by the Earth.
Yes.
So one Langley is equivalent to 41,840 joules per square meter.
Okay.
So
thank you.
What's a joule?
Right.
I wouldn't have been able to tell you that off of the top of my head, but yeah, you can convert it to joules, and that's Joules, not Jewels. You can convert it to joules, you can convert it to calories, you can convert it to BTUs, etc.
Right.
Or conversion formulas for all of that.
So I guess you were using it because it's specifically about, solar heat, and when geologists were looking at the energy paradox, like how do you melt all this ice?
Right.
They're thinking about it in terms of Langleys because of the sun. So
yes.
Okay, makes sense.
They're thinking about Langleys because in terms of radiation.
Right.
So,
all right.
Yeah. So anyways, Mills points out, and he says, many authors have inferred that these features were formed by periglacial action during the Pleistocene. So, boy, there's all of these weird features, these big blocks, these debris fans. There's all of this stuff. We're not really interested in this stuff. We're not really interested in its origin, its genesis, because we're looking at the bedrock and mapping the bedrock. So it's, it satisfies our requirements to say, well, it was produced under different kinds of conditions. So undoubtedly it was during the Ice Age. And because of the proximity of the great ice sheets to this region, it must have been periglacial. That was kind of the thinking, and as far as it went. Then Mills goes on to cite the work of Hackett, Hack, and Goodlett, and Greita and Bartholomew, who we have not quoted because I don't have their paper. But they argued, so this was 1960, and then jumping ahead 17 years to 1977. They argued that processes not associated with colder climates might form such features. They have suggested that such fans may be formed by debris flows set off by rare catastrophic rainstorms. So to me, the significance of that is now they're moving into the direction of being able to come up with an alternate explanation. Because periglacial phenomena wasn't really an explanation. It was just sort of a convenient way to say, okay, well, different times, glaciers close by, somehow that was the result. So you got freeze-thaw, which is a common periglacial. Now, this is not to say that freeze-thaw wasn't a process in initially causing the fracturing or the separation of material that could then be quarried or excavated by fluvial processes. You see what I'm saying? This is not to say that periglacial was not a factor. It very well could have been. But it's very difficult to say, okay, well, a periglacial process of freeze-thaw, for example, it could cause fracturing of rock in situ, in place. But then how do you get that rock from here to 5 miles away down the creek valley? How does freeze-thaw do that? See, there's the problem. And then Mills goes on to point out, and this is 1981, that dramatic support for the fluvial transport hypothesis was provided in August 1969, when Camille dumped up to 28 inches of rain in 8 hours on parts of central Virginia, setting off hundreds of debris flows. Now, as we talked about, the significance of that is that here you have the greatest modern catastrophic rainfall in this region, and it's being used to provide an analog for these much greater, vaster, more widespread deposits. Yeah, 88, and I remember reading about this. The rainfall was so intense during that Hurricane Camille that birds sitting on tree branches drowned because the rain coming down was more like sheets of rain rather than drops of rain. So that takes a rainstorm to a whole nother level. Then he goes on to say that accumulations of large boulders, often called block fields or block streams, are common on Grandfather Mountain. So we're going to start by looking at some pictures of Grandfather Mountain. And elsewhere in the southern Appalachians, wherever resistant bedrock and steep topography occur. Most authors have cited these features as evidence of former periglacial conditions. Although certainly suggestive, however, block fields and streams are by no means proof of such conditions. In fact, debris flows resulting from catastrophic rainfalls could theoretically move boulders of virtually any size down slopes. So there we go.
There you go. And it's Appalachians.
Okay, thank you. Every time I say it wrong, I want you to correct me.
Oh, man.
Well, yeah, it's going to be tough, I know. But the Appalachians, my apologies to all of the denizens of the Appalachians. Because, see, I should know that because, like I said, I have ancestors that settled the southern Appalachians. Okay.
Got it that time.
I got it that time, yes. Large block fields that are treeless or only sparsely covered with trees and shrubs are common features in the central Appalachian Mountains. Block fields of the Appalachians have been traditionally considered relics of periglacial climate. But then he makes the point that he's quoting Smith from 1953, stated that the conditions necessary for the formation of block fields no longer exist. So I think we can all agree on that, except with rare exceptional events like the Camille flood of 1969. Okay. So then let's look at some pictures. And again, it's pointing out that, these features, particularly like the debris fans and things, they're being eroded today. They're not being created. These are relict, R-E-L-I-C-T, relict phenomena, meaning they formed, it's like they're fossils, but they're on such a scale that no processes have had the power or the force requisite to alter them much since they were created.
Yeah, so while you're pulling up pictures, it kind of reminds the question of, how big of a boulder could the water move? It sort of reminds me of that Archimedes saying about the lever, right? Give me a large enough lever and a fulcrum on which to put it, and I can move the world.
Mm-hmm.
You give me enough water and a slope on which to run it, and you can flood the world out.
Let's see. We'll maybe be jumping around a little bit. Let's take a good look at this picture. Now here we've got slabs. So undoubtedly this rock, which I think a lot of this, but not all of it, but a lot of it was limestone with bedding planes. And so when it's being plucked and quarried, it's going to be typically plucked along a bedding plane, and that will produce these flatter slabs. But notice the imbrication in here. Like, look right at my feet at these rocks I'm stepping over. You see the imbrication there?
Oh, yeah.
Yeah, it's not, it's running like perpendicular to the
well, that
stream
could
flow.
be partially an illusion, but that's possible, because remember now, the water is not moving in straight linear lines.
Right.
It's back and forth, and it's meandering. So, if it's going around a bend, which I think this is actually in a bend. So if you can picture, there's somebody standing right here, the water kind of coming from more to the left and curving around. And so that water is curving around, and that's what's stacking these rocks up here like this. Now, rocks of this size could actually be moved by historical floods. But then when you start getting into this size, they're not going to be moved with regularity. And then the other feature that we see that is a relict feature is potholes. And when you see block fields and block streams associated with potholes, I think that's a pretty convincing argument that you're looking at relict landscape features that were produced by ancient large floods. Okay, so this is Boulder Deposits, Upper Tuckasegee Ridge, Upper Tuckasegee River. And you can see we're getting into some pretty good-sized boulders here. A giant pothole approximately 7 to 8 feet in diameter along the headwaters of the Tuckasegee River. Now, the Tuckasegee River is in North Carolina. So this is not being formed today. Potholes are not being formed. They're being destroyed slowly. But I would argue that they are formed rapidly and destroyed slowly. Now look at this. Notice potholes drilled into the bedrock. Notice the shape, like right here. Let's see, I think we could, right here. You can see, you see this circular arc here is matched by a circular arc over here. And then look at the boulders choking this constriction up here. So these boulders were being swept along. They hit this constriction because probably some more resistant bedrock here, and they got choked. They got jammed into this constriction right here. And so I think it's a pretty clear situation that the transport of the giant boulders and the potholes were the same phenomenon. Here's the giant
Yeah.
boulders along the Broad River near Chimney Rock, North Carolina. So, when you're looking at these and this is probably close to 20 feet along the long axis here. And look at this behemoth sitting back here.
Yeah.
So how did those get there? Right? The modern river did not move them. Even probably the greatest historical flood did not. It may have caused some movement within these, but it didn't pick them up and transport them.
One drop of water and one boulder at a time.
Yeah, there we go. So these are all just many examples. These are the kind of things that you can see all over the Appalachians once you go get away from the trafficked area and the roadways and stuff and get up into the creek hollows. You see this? I mean, look at this. This was not drilled by modern floods. This was an exceptional event that drilled. This thing is 4 or 5 feet deep into the bedrock. This was an amazingly turbulent flow that was sustained long enough to drill this thing into the bedrock, but then, it's over. Now it's a fossil feature. Now, this is interesting because you can see the texture of the rock. The rock has been molded by these erosive and the shear forces of this frictional mass of moving water going across the rock. In this case, from left to right. No? Yes, I think from left to right. But notice the texture of the rock surface with the pothole. And then we have Nakalula Falls, Alabama, with the extreme undercutting. Now, do you think that this feature was carved by this water flow here?
I don't think so. But what causes that? Is it swirling under there? Is it or is it an undercut from a bigger waterfall?
No, I would say it's turbulence. It's swirling. It's
Yeah.
So it's completely filled with water.
Oh, completely
completely
filled.
filled, and that water's spinning or something, swirling there, and it cuts that.
Well, and then you look downstream of Nakalula Falls, and this is what you see.
Oh yeah.
Wow. Okay, now I would say that no modern floods put those boulders there.
Right.
Now, let's see. I have
Is that Brad?
I believe that is, it could be Brad.
Did you Photoshop him in there, or is he really standing on the edge of that boulder?
I think he's
on the side of it.
I think he's
Looks like he's lying down.
That's what I'm saying. That's huge.
And then there's no way that these, I don't know, rolled down a mountainside or something. They definitely came from upstream.
Well, I'll tell you what, let's look at the next diagram.
Okay.
And you see, we're actually looking at we've got deposits that I would say it's a combination of both. But take a look at the next slide here.
Oh, yeah.
You can see the creek channel here. The falls is right here. And then this whole channel has been eroded out. And for a mile down, look at the boulders that you've got littering the floor of the channel. So clearly this is a catastrophic erosional event here. And the water that came through, and you can actually see the fluvial texture of the landscape when you look at this. Now this is from the is
that a LiDAR image?
Yeah, I think so. That looks like a LiDAR to me.
Yeah, let me show you. This is we'll go to it's the national
USGS natural 3D elevation.
Yeah, so we'll pull that up. Let's see here, Gadsden. There we go. Pull this up and share. Okay, so there we go. Yeah, let's see. Okay, I'm going to zoom in, and the falls is right here. So, and look, you've got even boulders up in this little tributary channel here. Now, were those boulders back flooded, or I don't know, but we're only seeing those big boulders we were looking at. That's this cluster right here, right there. And the falls is right here. So yeah, I'm going to say it's a safe bet that during the peak discharge, this entire channel was filled more than brim full. And that, in fact, you can see the texture of flowing water over the whole landscape here. Pretty impressive, I would say.
Yeah. It does seem like they've been breaking off that rim, but still
Yeah.
the water cut that whole channel.
Oh, yeah.
Yeah.
And look, you can see how this flow comes in, curves around this way.
Yeah.
It comes off, so it's undoubtedly doing a massive eddy current.
I see. Yeah.
Right here, like this,
Okay.
and then flowing down. And as it's doing, it's plucking off these huge blocks and washing them downstream.
Right.
And that's
So,
bedrock right there above the cataract. So there's all kinds of interesting little patterns and micro channels and interbraided things. It's really interesting patterning there on that bedrock right there.
It is, yes. So if we zoom out, you can actually, let's pull this out a little bit where you can see the topography that's going on here. This is part of the valley. This is actually, pull it out where you can really get the view of it.
That's just off the south side of the map behind me.
Yes. Now notice this. This is actually the southern end of Lookout Mountain. And the northern end is all the way up here near Chattanooga. So this is the so-called Valley and Ridge Province. So this is interesting because the Nakalula Falls is right at the south end of this trough. So you can see that any rainfall falling on top of the plateau here is going to be funneled down into this trough. And it's all going to be coming down here to the south end. And that's where we see the falls cut in right down here. And then the water would have flowed out onto the valley floor. And ultimately transported to the Gulf of Mexico, down this way. But this is all part of this very interesting Valley and Ridge Province that we can see goes all the way up. All the way up. Now this is folding. This is compressional folding. This has created this accordion type landscape. However, I think the evidence is pretty striking that this entire province served as a conduit for major meltwater flows, probably combined with flows produced by torrential rainfall. If we go all the way up, you see we're still following it all the way up. Keep going. We're up through West Virginia now. Keep going. We're now up into Pennsylvania. And once we get right up to here, guess what? Here's the margin, the southernmost margin of the ice sheet is right in here. And so you've got distinct, basically all of this ice that was over the Adirondacks here. When it's melting, it's flowing down this way. It's also flowing into the Hudson. And when we look at this topography here, we really can begin to see the fluvial sculpting. And something else that is very interesting to me is the water gaps. How do you explain those water gaps? Well, the old explanation is that, must have been originally lower, and then as the ridges are upraised, they're being upraised at the same rate that the river is down cutting them. So they're slowly uplifting, and then the river is slowly down cutting. And the processes are working in tandem at basically the same rate. However, I would suggest that perhaps there's a more effective explanation that calls on cataclysmic flooding. And for an analog to that, we go out to the Channel Scablands of Washington, because we can find places where the Palouse River is a perfect example of a case where the water breached a divide, a pre-flood divide. And when the flood was over, the river had been captured into a totally different channel. But yeah, so these are water gaps. And we're going to look at those water gaps.
But yeah, it is interesting that it's flowing basically perpendicular to all those ridge lines.
Yeah, why is it cutting right through the ridge lines instead of flowing around them or parallel to them?
Flowing along them or something, yeah.
Yes. That's the whole problem. And so now we get up here and you can see this stuff grades into a glaciated landscape here. So when this is melting, it's feeding water into this valley and ridge province. So we've got more studies to do here. But the Susquehanna River, interesting the way it cross. Look at how it cross cuts. Here, 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 here. What's that? 1, 2, 3, 4, 5 water gaps.
When you were just by the Delaware water gap, which has a major interstate through it, so a lot more people may be familiar with that, just northeast of there.
Yes. In fact, I think I've got some photographs of that I took when we went through there, and we were actually able to identify what appeared to be high water marks. So yeah, I mean, God, what an interesting landscape this is.
And bear in mind, the Appalachians are
Appalachians.
Okay. Appalachians are coal country all throughout the entire thing, from Pennsylvania down to Birmingham. Massive deposits of coal.
Of course, the coal is much older than the erosional events that we're looking at here. But so is the accordion effect, is very old. But because the actual formation of the ridges and the valleys is old, does not rule out the fact that there was a major erosional event that's very young. See? But yeah, so that whole, I'm suggesting that this whole area acted as a conduit for meltwater flow to the south that was also augmented by extraordinary rainfall.
Yeah, I understand that it's a folding area or whatever, but it looks like it's been accented or etched by other processes.
Oh, totally. I totally would think so.
Like it's sort of brought out the underlying structure.
Yes.
Yeah.
Yes. Brought it into, well, it's probably done a couple of things. I would bet I know for a fact that a lot of the valley floors are thickly filled with alluvium.
Okay. So it's fill them in and yeah.
Mm-hmm. By the way, that where you've got your cursor right now,
mm-hmm.
And I don't know whether you can say that is a massive sand deposit or not, but that is known as Sand Mountain because that whole plateau is basically a massive sand and sandstone.
Right. Now think about what we were talking about earlier when we were talking about, Hurricane Ivan coming up, spilling out over the creek channel here, just a few miles from my house, spreading over the floodplain and leaving as a sort of a calling card of its passage, this brand new layer of sand, right? So in other words, that sand was put there by being submersed in water.
And this Sand Mountain happens to be at the bottom of that whole chain.
Yes. So it's very possible that this whole area was submerged underwater. It's also very possible that the troughs of the valley and ridge were deepened during these events. And I'm not saying that there was just one. There may have been multiple events going back.
Yeah.
Okay. Well, then you've got all this, the Alabama River down here, which flows into the Gulf. So that's where ultimately, if water being channeled down the valley and ridge is ultimately going to cut its way through this area of hills. And this looks like, and then over here, the Chattahoochee River was probably one of the major conduits. The Alabama River looks to be the largest scale. conduit for the delivery of this meltwater into the Gulf of Mexico. I say meltwater, it could, also have been rainwater. Whatever the ultimate
Mobile
source
Bay there.
Mobile Bay, yeah, right here.
Yeah, the Alabamas actually starts in Montgomery and then goes south toward Mobile. In Montgomery, the Alabama is formed by the confluence of the Tallapoosa and the Coosa.
Uh-huh. Okay. Yeah, there's
they're both coming down off that whole plateau area.
Yeah. Okay. What was the other one besides the Coosa?
The Coosa is to the east and the Tallapoosa is to the west.
I see it. The Tallapoosa northwest from there. Or northeast. Is that it?
Yeah. Okay. There's the Tallapoosa
right.
And there's the Coosa. They're both coming down right here. And then it becomes, I guess that's the Alabama there. Yeah. Okay.
Yeah.
And then further west, you've got the Tombigbee.
Right.
Yeah. So it's clearly a huge watershed.
They all feed off of come off the Tennessee Valley river system.
Yeah.
Well, Coosa goes through Wetumpka, so you might as well zoom in on that and just tease a future topic show there.
Okay.
Oh, yeah.
Okay, I can do that. Coosa, let's see.
So it'd be just north of Montgomery there.
Yep. It's down at the bottom of your screen.
Okay. There it is. Okay, and then the Coosa River. So Wetumpka would be north of Montgomery.
You were about at it. It's just north of Montgomery there.
Okay.
Bottom of the screen.
I got it right there, Wetumpka. All right, so let's put back our. Can we actually see it?
I see it.
Yeah. See the crater rim?
Oh, of course.
There you go.
There it is.
Yeah, there it is. Yeah, I tell you what, I'm just, I need my CBD oil.
And we discussed, when we were over in Woodland, talking about all the springs around Woodland.
Yeah.
There are springs around the edge of the Wetumpka crater as well. There's one well-known one's a big private swimming pool there called Willow Springs. So that whole area is full of water features.
Yeah. So, let's tell people what we're talking about here. Wetumpka is an impact. It's an astrobleme. It's the remnant of an ancient impact.
Yep.
Brad and I made one excursion there. Probably could make some more. I mean, I think we should organize some tours to go there because there's actually been some new studies since we were there that have documented some outcrops that we were looking for and couldn't find. And there's now actually a field guide available to the crater formation. So it would be great to get that. Yeah. Here you can see it. Look at here. This river. This is what river is this one right here that's wrapping around the rim of it? Small river, but you can see
that. It's just some creek. I don't know the name of it.
Okay. So there it is. You can actually see the circularity of it. You guys, Russ and Kyle, can you see that?
Oh yeah.
It took me a while. And I've looked at it 10 times if I've looked at it once. And that's why I don't know. I guess I'm losing it, guys.
It looks cool. We should go there for sure.
Yeah, we need to
go. It's midnight.
Yeah. Right up there, that little lake is midnight.
So that was a place we considered including on our trip that's coming up, our Lower Cumberland trip, but it's just a bit south to do that dog leg. So there's enough other things to the south, southwest Georgia, and then Wetumpka there, and then you have the Moundville, Alabama, which wouldn't be far. So there's another backyard tour in the works there that would include this site right here.
And as I'm looking over here at the landscape, you can see the fluvial shaping and sculpting of the land.
Oh, yeah.
Look at that. That's pretty impressive. Because, as people I hope are beginning to appreciate, we've got some pretty amazing stuff right around here that's worth looking at. So I'm going to stop that share. I'm going to go back to some more photographs.
Yeah, we probably ought to wrap
Wrap
it
it
up
up?
here pretty soon. Yep.
Yeah, okay. We will go 5
Now,
more
is there a name for that massive feature that runs all the way up and down that we've been looking at this whole time?
the Valley and Ridge Province.
Valley and Ridge Province. Okay.
Yeah. All right. Deposits along the Bluestone River, West Virginia. Now, this is, you're going to see smaller stuff here. Now, a lot of this can certainly be transported by historical scale floods. But typically what the historical scale floods are going to do is they're going to move this stuff down slope, but it's not what originally deposited the boulders. And remember, when you've got a stream flow and it begins to slow, like you've got a flood and the peak flood begins to subside, what'll happen is the first and largest clasts, CLASTS, are deposited first. And then you get successively smaller rocks and boulders as you go downstream. And here's a good example of where you can see how the modern forest is slowly encroaching and concealing the ancient boulder deposits. So many of these valley floors are mantled with this stuff, but it's not readily apparent because the last 10 or 12,000 years of ecological succession has obscured them, starting with the layers of soil, then enough soil that you can have tree roots, and then the trees begin to form, and then pretty soon this becomes a subsurface layer. And you wouldn't know it was here unless you excavated down or you had a stream that was able to, keep excavating and exposing the banks of the stream to show you what the architecture of the subsurface landscape actually was. Yeah, so here, this is a good one because you can see here was where the glaciers came. We think that the glaciers came and terminated at the heads of the Finger Lakes and then came down and pretty much buried the Adirondack or Allegheny highlands here. So when they melted right here like this, how do you explain that?
Wow, that's awesome.
This will be on one of our future tours.
Giants.
Yeah.
That's how I explain it.
Where's the troll?
Yeah. Pretty amazing, isn't it?
Yeah, that's beautiful.
I know. Thomas Jefferson once owned this bridge.
Wow.
And they say also that George Washington did some of the surveying around there, and there was like a peg in the ground from George Washington.
I
remember something like that. Yeah. And that was probably 180 feet high. Do you remember? Is it that big?
Yeah.
It's really impressive.
I think it is that big. Yeah. And let's see, we'll jump backwards a little bit here.
There we go.
Cumberland Falls. All right, so it's your typical alcove, your horseshoe-shaped falls. Notice the texture of the bedrock. Again, it's been sculpted fluvially. So you've got just now, like with the Nakalula Falls, notice you've got the falls itself, you've got the cataract, which you can see right here. See the horseshoe shape. And then below the cataract, here's some of the boulders you've got. Look at this thing.
Man.
Yeah. So this is kind of an indication of some pretty extraordinary stream power that's left this in its wake. And I think it's safe to say that the modern floods on the Cumberland River have not been responsible for putting this deposit of boulders here. Look at this thing. And look at this scouring here. You can actually see the vorticular, the turbulent sculpting that was probably, so most likely here what you had, was, pothole erosion being drilled into the rock, and then subsequent to the pothole being drilled, the boulder was actually fractured away from its bedrock. It undoubtedly didn't get transported far. This is probably a football field or so below the falls. So it was probably, quarried out of the bedrock at the time the falls was created. And then you look across the stream and you can across the river and you can kind of get a sense of the scale of these things. So look at the whole floor of this is mantled with these gigantic boulders. We've already looked at this, so I'm going to skip past that. And then we look at an example of imbrication. And so now you know that imbrication is a paleocurrent indicator, and clearly here, flow would have been left to right. And here we get Boone Fork Creek, North Carolina. Boone Fork Creek is on the flanks of Grandfather Mountain. Notice the water flow here. I think we can safely say that this water flow did not put these giant slabs here. The biggest floods modern on here, what they're probably doing is perhaps moving these slabs, but not really picking them up and training them and washing them downstream. But you can follow these creek valleys up for miles and they'll be choked. Let's go back to the quote from Daniel McCallick when he says, as you're looking at this picture, it is further difficult to conceive of a discharge of water, regardless of the severity of the storm responsible for the runoff, sufficient to have choked some valleys with the tremendous boulders that now block them. Notice the people for scale. This is the Little Pigeon River in the Smoky Mountains. Big Creek in the Smoky Mountains. Look at these boulders. These are 6, 7, 8 feet in diameter. And notice the rounding tells us that they have been transported and rolled. Do you remember this day, Brad, when we hiked up here?
I sure do.
That was, I remember that day as being a really wonderful day. And what really impressed me, what I came away with is we're hiking up along a big creek, was how refreshing it was. The water rushing down, and it was a cool day. And I just remember I had this feeling of almost rejuvenation as we were hiking up along this creek here. And the sound of the water, and I suppose the negative ions being produced by the rushing water, and I don't know, it was a beautiful, It was a beautiful summer day, and I just have this outstanding sense or impression that I carried away from that particular hike that day. And then we get to this extraordinary example of imbrication along the Big Creek, Smoky Mountains. We need to get back here. And maybe, I wonder if we could get, time's running out. Before we know it, winter's going to be over. But really, this was a summer trip, and we need to be up here in the winter where we can really, see these boulders as much as possible free of vegetation.
Let's go.
Oh, well, okay. So, yep. So here's the takeaway from here. We're looking at wreckage. It's like, imagine it, you got an old building and somebody comes in with the wrecking ball, smashes the thing to bits, and you've got a pile of wreckage there. So for a long time, that building might have been sitting there vacant and slowly decaying, right? slowly, eroding. But then somebody comes in with the crane and the wrecking ball, and boom, in a very short period of time, the amount of work done on that building far exceeds in orders of magnitude the work that was being done slowly upon it by the normal forces of wind and rain and so on, right? We're looking at wreckage here just as much as if you came in the day after the work of the wrecking ball was done and you looked at the pile of wreckage there. That's really what we're seeing here. We're seeing the debris, the wreckage of the former world that existed here, and the energies that was required to create this massive wreckage are almost inconceivable. I mean, if we were going to try to duplicate something like this today, how would we do it? Well, how about an all-out nuclear assault on the Southern Appalachians? Something like that is the types of forces we're talking about here. And the modern creek, look, it's flowing right here. It did not create what you see here. It did not leave this mass of these huge boulders lining these valleys over thousands of square miles. It did not create this pothole erosion that you see here that we've been looking at. It did not drop this boulder here. So, yeah, check this out. So here's the map of the Nakalula Channel. There you can see the falls right there. Watch this now. See, so all of this stuff, it's hidden. That's another part of the takeaway. So much of this is hidden from normal view. And now with technologies like LiDAR, we can see what's underlying, what lies beneath. We can actually see. And there you see the southern portion of Lookout Mountain.
I'd be interested to see some dendrochronology on the forests or something in that channel. I mean, there look like there's some big trees in there.
Oh yeah,
or something.
Isn't that what? Sorry, go ahead.
I'm just thinking of like how to date we had talked about this before, but just how to date all of the organic materials, like the modern forest, getting to the bottom of the soil buildup and all of that kind of stuff. Is there a way to kind of look back and see, well, when did this?
Yeah.
When was the last time this channel was cleaned out? In other words.
Well, see, the thing is that it may have been produced. There may have not been a clean out. In other words, it may have been eroded. Then, alluvium, flood transported alluvium dumped in there. And then it's been sitting there. And then you have the ecological succession of trees growing. Who knows? Maybe at one point it was the timber was extracted. I don't know the history, but what you'd have to do is go in and get a lot of samples that have organic datable material in them. And then if you had 100 samples and you had a range, say, of 5,000 years, because of flood coming through that's exhuming landscapes that have been buried for thousands of years, well, it's going to have much older material intermingled with younger material. So you need to have enough samples that you can find consistently a younger date or a youngest date showing up.
Right.
And that youngest date is going to be the probable date of formation. So there.
What I was going to throw in, heard several variations, I guess, of the word definition of the word apocalypse. But one of them is along the lines of a revealing, or that all things hidden will be revealed. So we're seeing the Earth's surface and reading it and what it's telling us. It's being revealed to us. It's been hidden. The story's been hidden, but we're getting to see it now.
Yeah, we are. I mean, what we're doing here and what we're actually trying to do with this podcast is to cultivate a vision here so that people can begin to see this stuff that has been hidden from our view, both because it's literally obscured by 10,000 years of Holocene landscape development, but it's also obscured because the scale of it is so vast and our perspective has been so limited that we haven't been able to see it. But now that we're literally becoming a spacefaring civilization and we have we have a planetary perspective now, we're sort of in a privileged position is that we can begin to see this phenomena now in a way that no previous generation could. And I kind of like to think that what we're doing here is kind of in the forefront of the effort to reveal what has been hidden for 10 or 12,000 years from human eyesight.
You bet.
Absolutely.
So on that note,
Yeah.
Hopefully it comes like a flood and strips away all the BS so that we can see.
That's right.
yep.
Do it. So we are in the process. So we mentioned it about moving the podcast to HowTube. We are going to be hosted there soon in the next, couple 5-6 episodes. We'd like people to start watching it on the website itself, randallcarlson.com. And of course, once you're able to join HowTube and follow us there, that's going to be coming up soon, and that's going to change the way we do the advertising. It's going to greatly increase what we can earn from this to support what we're doing and the growth and the new things that we want to do. So that's going to be better for us over there. So we're really trying to get people geared up to make that switch with us. And then also I want to thank all the people that continue to write in and send us really interesting stuff. People ask great questions, and I hope they're taking it upon themselves to find those answers and not expect Randall to be able to answer all of them. We've got like retired engineers and people that have some time and have gotten really interested and are sending some really detailed work to us. That's awesome, but we just don't have a way to process it or know exactly what we can do with it right now. But I don't want people to stop sending us that stuff.
Correct. Please don't.
Yeah, again, the best way is directly into our podcast email, the Kosmographia1618 @gmail. There's also several emails we brought up, research at randallcarlson.com, tours at randallcarlson.com, and also volunteer at randallcarlson.com to send us emails directly and help us sort some of those contributions that people are sending in. And we're going to eventually have a system and a staff, and Randall certainly needs assistance, and we're going to be getting more of these things and figuring out how to continue building this community and get people involved and keep them involved and continue this revealing.
Yes. And we're going to also be segueing into some other things. Geology will be always a consistent underlying theme, but we'll be getting more into astronomy. We're going to be getting more into symbolism, and we're going to start looking at some of the ancient traditions, because we've been, referencing a lot of modern scientific work and papers and research and so on. But I'm, a total, convinced that the ancient and archaic records can complement the modern records and fill in a lot of the gaps in our knowledge. And I hold a lot of these traditions that have come down to us from the past in very high regard, and believe that it can really help us to gain a deeper insight into a lot of these questions and these mysteries, and trying to piece together exactly what happened. And so we'll be getting into a lot more into that, looking at some of the many venues by which these symbols and things have come down to us. And that's going to be a really juicy, interesting part of what we're doing here when we start getting into some of that. So that's coming up, but stick with us through the rest of this geology. We would like to at least get the groundwork done that shows, at least, at some point we will of course show that, we're looking at a planetary wide phenomena. We're concentrating on, obviously North America, because we have done most of the exploration and travel and field investigation in North America. But hopefully in the near future, pretty much no matter where you live on the North American continent, you're going to know that these cataclysmic features, you're living right on top of them, and they're all around you. So, yeah, a lot more to come. And please don't object if we start actually raising revenue through advertising. We're going to vet any advertisers who come on board, that we actually believe in their product and the integrity of their product. But bear in mind that once that revenue starts coming in, it's going to allow us to do more. And what that's going to do is it's going to translate directly back into what we can deliver to you. And I think if things, if our strategy comes to fruition, I think this could get really interesting in the next year or two. So.
Oh yeah.
And it's
Thank you, everybody. And check the description, get the link, check out randallcarlson.com and get you one of those beautiful logo shirts like Silent Mike is wearing.
Mike, there we go. Puff out that mighty masculine chest of yours.
We've got white ones now. We've got a baseball cap with the logo on it coming. All kinds of different ways to support us, and more on the way. Thank you, everybody.
Yeah, thanks, everybody.
Yeah, and Randall, I agree. The geology is the groundwork.
That's right.
Right?
Yeah.
I get it.
No pun intended.
I totally get it. All right.
Thank you,
Till
Randall.
next week. Yep.
Good night, guys.
Thanks.
Good night, everybody.
Yeah.
See you next week.